The ABC of galaxy evolution. In other words, there are three critical factors that determine how galaxies are the way they are. So when we look out into the universe, we see all sorts of interesting galaxies. Some grand designs like this sort with a very large bar across the middle. Sometimes we see galaxies that appear to be very distorted. This looks like it might want to be a spiral galaxy, but the proximity of a neighbouring galaxy is distorting it somehow. Some galaxies appear to have a lot of arms, some appear to have a couple of arms and a very pronounced bar through the middle. But we can ask the question, what are the basic influences that determine the particular structure and the collection of galaxies, either individually or in clusters or superclusters? And the ABC outline the three principal factors that dominate the evolution of galaxies. A is for accretion, because galaxies form by matter accreted under the influence of gravity. Matter created in the Big Bang eventually accretes and forms galaxies in a way that we will see shortly. And we know that the centre of either every or at least most galaxies, there appears to be a supermassive black hole. Certainly in most of the galaxies that we've studied to date, there appear to be supermassive black holes, possibly millions of solar masses, and in some cases up to many billions of solar masses. Some of these black holes are very active, in other words, they're feeding on the matter around them, and some black holes, like the one in our galaxy, is relatively quiet, quiescent, and apparently not a great deal of matter is falling into that supermassive black hole. And the third factor of the ABC is the C for collisions, because galaxies grow by collisions with other galaxies. Galaxies merging together determines the way galaxies evolve from their creation through to how they look now and how they will look in the future. So those are the ABCs that we're going to be talking about this evening. So where does the story start? Well, it starts at the beginning, like all good stories, and it's the beginning of everything. So a few years ago, I think it was 3 years ago, I talked about the beginning of everything and said that everything that we currently see in the entire observable universe, which at the moment is a sphere about 100 billion light years across, because we believe the universe is expanding, and hence if we wind the clock back, everything used to be an awful lot closer together, we can deduce that everything that is currently inside that 100 billion light year diameter sphere that we call the observable universe, all of that stuff used to be separated by only centimeters. Hence the idea of a very early cosmic golf ball. A cosmic golf ball that has dimples in it, and those dimples are the small variations in density and pressure and temperature that ultimately gave rise to everything we see in the universe. Those dimples, or those imperfections, those small variations, are what we see imprinted on the cosmic microwave background. So it's a relatively uniform microwave background, but there are small variations which here have been exaggerated in terms of the colours. Red and blue indicate a small excess or discrepancy of the actual intensity compared to the average. So it's essentially the same everywhere, a temperature of just a few Kelvin, but there are tiny variations of order less than a millikelvin in terms of hot spots and cold spots, as indicated here. And that variation in the cosmic microwave background is a result of those small dimples in the cosmic golf ball. But we can ask, well, okay, how did that come about? Yes, small variations in the original tiny universe that was only a few centimeters in diameter ultimately got imprinted on the cosmic microwave background. But how did those density variations ultimately give us a universe full of galaxies? When we look out into the universe with something like the Hubble Deep Field, we see thousands of galaxies in a tiny patch of sky. That tells us that there are many hundreds of billions, possibly even trillions of galaxies within the observable universe now. Well, you could argue that everything we understand about the evolution of the universe on the largest scale, and perhaps not everything, but certainly a large fraction of what we understand, is the result of simulations. Yes, we can make observations about what the universe looks like, but in order to figure out, can we understand how the laws of physics gave rise to the universe that we see today, well, simulations have helped enormously. And computing power, you could argue, really wasn't up to the task until relatively recently. In other words, many decades ago, computers simply weren't powerful enough to run simulations where we could say, yes, we think we've built the physics into these simulations and we can believe what these simulations are telling us. There are lots of different simulations out there. I haven't got time to talk about them all, but I am going to use the results of one particular set of simulations called the illustrious simulations. I'm going to use those to illustrate what I'm talking about this evening. So, how did the dimples in the golf ball, how did the small variations in density in the very early universe, which got imprinted on the cosmic microwave background, how did they, over billions of years, give rise to the structure that we see in the universe? A universe full of galaxies that exist in clusters, that exist on filaments in a very large web structure, the so-called cosmic web. We can see that if we run one of these simulations. So this is an illustrious simulation in which we're taking not the entire universe, but we're taking a relatively large cube, and we're just seeing it as viewed from one side here. We're taking a large chunk of the universe, filling it with matter and putting in small variations in density. And then we're just going to say, let gravity do its stuff. And in this particular simulation, a dark colour represents low density and a bright colour represents high density. So at the moment, you can perhaps see just a little bit of mottling in the blue colour. But let's run the simulation and see what gravity does to this over billions of years. The dense regions get even denser and the not so dense regions get less dense. And you can see we have some bright white areas indicating high density, where gravity is getting hold of the density variations in the original cosmic golf ball, and over time it pulls those high density regions together and forms ultimately the concentrations of matter which give rise to the galaxies, the clusters of galaxies, the superclusters of galaxies. And we notice that they don't occur randomly. We notice that galaxies tend to occur in lines, in these filamentary structures. And also we notice some regions, for instance over here on the right-hand side, some regions which appear to be essentially devoid of any structure, essentially devoid of any galaxies or clusters of galaxies. So we end up with a web type structure where we have voids and we have filaments and we have knots where filaments join each other, where there are very high densities. And this is pretty much what we see when we look out into the universe. We see galaxies that aren't uniformly spread throughout the universe. We see this sort of filamentary structure. So the fact that simulations are capable of reproducing this large-scale structure in the universe gives us some confidence that these simulations appear to be doing a good job. They work by basically indicating that as gravity takes hold of these density fluctuations and starts producing this structure, matter flows through these filaments, and where the filaments join, that's the nucleation site for clusters of galaxies. Matter flows through the filaments. It's not a question of simply they come and at random the filaments form. As the filaments start to form, matter effectively gets funneled down the filaments into the knots between the filaments, and so matter starts to accumulate in these areas, and that's where we get the early formation of galaxies, the proto-galaxies if you like. But the simulations are not quite as simple as I was implying. It's not just a question of throw a lot of matter into a large box and tell the computer, let gravity do its stuff. you must also take into account, if you want to understand how galaxies form, you have to deal with the small scale structure of the universe as well as the large. You have to take into account that when galaxies start to form, stars are born and stars live and stars die. You have to take stellar evolution into account if you want to understand how galaxies evolve. And that's because although gravity is trying to pull everything together, as soon as you start making stars and as soon as stars die, well, stars could die through supernova explosions and they could form black holes, which then produce jets, which have outgoing matter and outgoing radiation. As soon as you have stars dying, you can have outflows that basically prevent the matter being pulled in by gravity and forming condensed structures. So although gravity is universal in the sense that it's always trying to pull in, it sometimes gets impeded by the process of stars being born and stars living and stars dying, ultimately producing outflows which prevents or at least impedes the infalling matter. So if you want to get the structure right of how does gravity form galaxies, you have to take into account stellar evolution. So evolution on stellar scales affects the evolution on galactic or galactic cluster scales. And that's one of the reasons these simulations are so complicated. You have to take into account structures on the largest of scales and, relatively speaking, the smallest of scales. So can we use simulations to explain essentially all the galaxies that we see? We know there are lots of types of galaxies. For instance, here's just a plot of typical types of galaxies that we see in the universe. The left-hand side of this particular chessboard happens to contain all the galaxies that appear to be disk-type galaxies. They tend to be bluer in colour and a lot of them have spiral structure. On the right-hand side of this diagram, there's a lot of galaxies which tend to be redder in colour or a little bit yellowish in this diagram, and they tend to be more elliptical in shape and not to have any particular spiral structures within them. So any simulations that we want to run that hopefully will give us an indication of how the universe ends up with the large-scale structures that it does, hopefully those simulations will be able to reproduce this diversity of galaxy types. So let's have a look at how accretion actually works. So I've said that the Illustris project is one set of simulations that effectively allows us to look at galaxy forming from essentially just after the Big Bang all the way up to the present day. We haven't necessarily run the same simulations into the future because we're running them up to the present day, because when we get to the present day we can say, do we get the universe that we see? We don't actually know what the universe is going to look like in the future, and therefore we can't run those simulations and say, yes, that's right, because we haven't got to the future yet. So the simulations tend to run from the Big Bang to the present day. And as I've said in the last couple of slides, it's not just a question of allowing gravity to do its stuff and allow matter to accrete. We have to take stellar evolution into account, the middle panel here, so that the generation of supernova and black holes can also influence the way matter is accreting. But we also have to take the left-hand panel into account as well. We have to account for the fact that there is actually more dark matter than there is ordinary matter, and that must be in the mix. Because if we don't account for the existence of dark matter, the simulations simply don't contract enough. In other words, gravity doesn't have enough mass to pull everything together to give us the large-scale structures that we see in the universe. So these simulations have to deal with a lot. They have to deal with dark matter, which is, there's a great deal of it out there. There's less ordinary matter, but the ordinary matter is responsible for making stars, which might ultimately go supernova and then ultimately forming black holes. So these simulations have an awful lot of work to do, which is why we need supercomputers to actually run these simulations. It is not a trivial problem. The illustrious simulations that I've chosen as an example, the original simulations ran for 20 million CPU hours. In other words, one CPU, central processing unit, running for 1 hour, multiply that by 20 million. That's how much computing power was used in the early teeny years here, 2013 to 2015, to run the simulations that I'm talking about. After those simulations were complete, they realized that it would be possible to tweak the simulations to produce a little better physics. In other words, a little more of the physics involved in stellar evolution to try and improve the accuracy of the simulations. So the simulations were improved. What would you call these improved simulations? Would you call them Illustris version 2? Well, most people would, but with a certain sense of humour, the people who wrote this code decided to call the second version of Illustris the next generation. You can see which sci-fi these guys like. So these simulations have become known as simply TNG for short, the second version of the Illustris simulations. And Illustris TNG ran for something like 200 million CPU hours in the late teenies from 2017 to 2019. And they, of course, ran on supercomputers in order that it only takes months to run these simulations. If you try to run essentially the same code on an average desktop computer, even a really fast one, then these simulations would take something like 20,000 years to run to give us the results that we're looking at here. Illustris TNG was carried out on different scales. Instead of trying to simulate the entire universe in one go, which would be beyond the capability of any supercomputer, what they did was run the simulation on a spatial scale of 300 megaparsecs, 300 million parsecs, basically taking a cube and looking at what the structure is on the largest of scales. But because galaxies are relatively small on a scale of 300 million parsecs, they decided that they would also want to run on a smaller scale. So they ran on a scale of only a few 100 million light years. In other words, 50 million parsecs. We'll remind ourselves of the relationship between parsecs and light years in just a moment. But in order to make sure that A, you take the largest scale structures in the universe, and B, you take into account everything that's going on in the smallest of scales, they ran the simulation on 3 different scales. The middle one, the so-called TNG 100, on a spatial scale of 100 million parsecs, to make sure that the data was joined up. In other words, everything they saw at the 50 million parsec agreed with the 100 and agreed with the 300. But you can't simply use all of the detail at the TNG 50 scale and simply run it for the entire 300 megaparsecs, because it would simply be too complex a code to run. So let's just remind ourselves about parsecs and light years. Amateur astronomers tend to use light years because there's a certain simplicity in the idea of how far light travels in a year. But astrophysicists tend to prefer using parsecs. And 1 parsec is a little over 3 light years. So to remind ourselves, the scale of the Milky Way, roughly 150,000 light years in diameter, so about 50 kiloparsecs. And the distance between galaxies, well, if we take the distance from the Milky Way to the Andromeda galaxy as a useful yardstick, if you like, that distance is about 2.5 million light years, or about 1 megaparsec. So parsecs are actually quite a useful unit, because roughly speaking, we can say that the separation of stars is of order parsecs, and the separation of galaxies is of order megaparsecs. So it's not strictly true in all situations, but it's a very useful yardstick. Stars are separated by parsecs, galaxies are separated by megaparsecs. And we can always convert into light years if we so wish, with this 3.26 light years in 1 parsec. So let's have a look at one of the Illustris TNG simulations. Here we're looking at, again, not the largest of scales. We're looking at an area where different filaments of the cosmic web are meeting. So in other words, matter is falling into this region that we're looking at. You see the scale on the left-hand side, there's 50 kiloparsecs, so we're looking at something that's galactic size. We're not looking at a huge cluster of galaxies or a supercluster of galaxies. We're looking on a spatial scale only a little bit bigger than one galaxy. And because we're looking at a point where filaments of the cosmic web are joining each other, matter is flowing in through a filament coming in from the top right, and also matter is flowing in from the bottom and from the left. In this particular illustration here, bright means relatively dense and relatively hot. And a darker colour, the darker blue, represents a less dense region. So let's run this simulation and see what it looks like. So matter is flowing in from the top right and from the left and from the bottom. And you notice that at first it's extremely chaotic, and some matter is lost and some matter is captured by this dense knot in the middle. And you can also see a certain amount of rotation is in evidence as well. And as the rotation becomes more and more pronounced, and notice that the corners of this image are getting darker and darker as more and more matter from the surrounding region is flowing towards the centre, and it's giving us something which is looking more and more and more like the sort of galaxy that we can recognise. We're starting to see the hint of spiral arms forming, and we can see that we've got very dark regions out here, indicating that a lot of matter has now flowed from these regions towards this central region. And we now have a structure which is looking like a spiral galaxy on a spatial scale, again roughly the same sort of size as the Milky Way. We can ask ourselves, okay, that's one galaxy, but the simulation is running, if we look at, for instance, the TNG 300, we see a filamentary structure. Here it's shown as dark on a light background rather than vice versa, and we can see the cosmic web is starting to show in this simulation. We can see some dense regions, and we can see clusters, and we can see filaments where lots of galaxies seem to be lining up along some rather wavy looking lines. But if we were to look in detail and zoom in to particular knots where we see individual galaxies, we can ask ourselves, well, do these simulations actually reproduce the sort of galaxies that we see in the universe? So here we have four panels that are simply zooming in to particular structures in the TNG 300 simulation. And when we ask, do they look the same as real galaxies? Well, those that we've got there do indeed bear some resemblance to real galaxies. So on the left-hand side, there's an observation of an actual pair of interacting galaxies, which look a little bit like this pair in the simulation. And similarly, we can see other interacting galaxies out there that look very similar to pairs of galaxies that we see in the simulation. And sometimes we see galaxies that look a little bit nebulous and have a faint ring structure, and again we see some evidence of that in these simulations. But if we want to see the finest detail within galaxies, then we shouldn't simply be zooming into TNG 300, we should be looking at the highest resolution with TNG 50, looking at a smaller box but seeing greater detail by looking on the smaller spatial scales. And a TNG 50 simulation should show us more detail of individual structure in individual galaxies. And if we do that and look at lots of galaxies, well, we see this sort of result. The left-hand side is a coloured set of images of galaxies that are shown in the TNG 50 simulation, and we're looking at where does the hydrogen appear to be in these simulations. In each case, we're looking at the galaxy face on in the top half of this particular panel, and the side view is shown below. So this little line is indicating that these are disk galaxies. At the moment, we're just looking at what these disk galaxies are looking like. So the sort of whirlpool that we saw earlier in the simulation, but as seen from the side, they look very much like a pancake. The right-hand side of these panels, in the grey, is asking the question, well, if the left-hand side is showing where all the hydrogen is, then where would we expect the star formation to be? And if we assume the star formation is going to give rise to a lot of the luminosity of this galaxy, we can ask, what would we expect the appearance of these galaxies to be? And the right-hand side in grayscale are indicating, in this simulation, what would we expect the appearance of these galaxies to be like? And I hope you agree that on the right-hand side, we see the sort of things that many of us have either seen or imaged in the universe. There are lots of galaxies out there, especially the disk and spiral galaxies, that do bear a striking resemblance to the sort of structures that we see in these TNG 50 simulations. And indeed, TNG 50 does generate quite a few galaxies which have masses of something of order 200 billion solar masses. In other words, they have something like 200 billion stars in them. That number is, roughly speaking, the number of stars in the Milky Way. So if the TNG 50 simulation does generate galaxies that are spiral, as seen by the face-on view at the top here, and look like pancakes, or if you prefer, two fried eggs back to back, as seen edge on. And if those galaxies appear to have something like 200 billion stars in them, then it looks like this TNG 50 simulation is indeed generating a lot of galaxies that are analogues of the Milky Way. If a simulation is capable of generating lots of galaxies, but none of them look like the Milky Way, then there is something wrong with the simulation, because we know that the Milky Way exists and we know there are quite a few galaxies similar to the Milky Way. So the success of the TNG simulations is the fact that they do reproduce the large-scale structure that we see in the universe. And when we look at the details of the galaxies that they produce, these simulations again produce a lot of familiar looking galaxies. Let's have a think about what's going on in the middle of these galaxies, these supermassive black holes that appear to be at the center of all galaxies. How do we know that? Well, one of the first inklings we had was by looking at what stars are doing very close to the center of our own galaxy. We know by observing them for decades that there are some stars that are very close to the center of the galaxy that appear to be in orbit around something that we can't see. And it must be massive in order to move stars in the sort of orbits that we see, and it must be relatively small. Otherwise, for these stars very close to the center of the galaxy, if this object wasn't small, then the stars would simply collide with it. So we know it's very compact, and yet we can't see anything. And for more than a decade, we've been watching stars as they orbit around something. They all appear to be orbiting around the same object. The object must be very massive in order for these stars to orbit with the periods they have, and it must be very small so as not to collide with any of the stars, or not have any of these stars collide with the object at the center of the galaxy. And simply from the laws of motion that we understand from Kepler and Newton, if we watch stars as they go around an object, we can work out what the mass of the object must be that are keeping them in orbit. And we calculate that the mass of this object must be some 4 million solar masses at the center of our own galaxy. And yet the object itself can't be any bigger than a few light hours. In other words, something of order the size of our solar system. It must be smaller than that. And just for brevity, I'm using this symbol M. Circle dot is simply shorthand for the mass of our sun. There's nothing special about the mass of our sun. It's just a convenient unit to use when we're talking about supermassive black holes. So we can deduce from the way stars are moving that our galaxy has a supermassive black hole, hereafter just SMBH, a supermassive black hole with a mass of 4 million solar masses. But we know of much heavier supermassive black holes at the centers of other galaxies. For instance, Centaurus A. It's not visible in this image, but we've deduced from the motion of gas and stars that this has a supermassive black hole of some 100 million solar masses. And that's by no means a record. For instance, the Sombrero galaxy has even more massive, supermassive black hole than this. But we can deduce that what happens when a star gets too close to a black hole, this simulation would show that stars can get ripped apart by the tidal forces. So there was a black hole lurking on the left-hand side that we might not have noticed to start with. But if a star gets too close, tidal forces can rip it apart. And we end up with this accretion disk, simply because all of the matter of the star can't all go down the plug hole at the same time. There's a conservation of angular momentum involved, which means you end up with a circulating, just like circulating water in a bathtub. The water doesn't go down the plug hole instantly, it circulates, and the inner part of the accretion disk will eventually go into the black hole, but the outer parts will be, in a sense, waiting their turn. But as the matter circulates around the black hole, all of the matter is interacting with all of the other debris that's resulted from a star getting ripped apart, and enormous amounts of energy can be released. So although it's not being released from the black hole itself, it's being released from the region just outside the black hole. Some of the energy is released in radiation and can form the jets as indicated by this particular animation. Exactly how infalling matter can result in jets that effectively come out of the spin axis of the black hole, the mechanisms by which that happens are still not fully understood, but it appears that lots of black hole systems generate jets in addition to the accretion disks. If we look, for instance, at the galaxy M87, you can see a little jet coming out in the bottom there. If we look at it in more detail with the Hubble Space Telescope, we can see a jet coming out of the center of M87. We think there's actually jets coming out in both directions. In other words, when you get one jet, there's a jet going in the opposite direction. But if one is pointing towards us, it will be a lot brighter than the one pointing away from us. And so we see one and not the other. And if we use radio telescopes in tandem, or at least a lot of them spread across the world, we can tie them all together to get, using radio interferometry, we can get the result of something similar to a radio telescope the size of the Earth by connecting together, or at least taking the data. It's difficult to do it in real time, so the data is collected from radio telescopes across the world, then it's all brought together, and then one extremely sophisticated piece of software basically correlates all of that data and produces an image that would be the result of having a telescope the size of the Earth. And that produced the supermassive black hole images of M87 and also the Sagittarius A star, the black hole at the center of our own galaxy. M87 was chosen as a target for the Event Horizon Telescope because it was one of the more massive supermassive black holes. It had already been calculated that this particular black hole has a mass of 6.5 billion solar masses, many times bigger than the one in our own galaxy. So it is assumed that this would be quite a large accretion disk, and it turns out to be large in the sense of physical size. Of course, M87 is quite some distance away, so the actual angular size of this accretion disk is not large. It's only measured in micro arc seconds. So that's why you need a telescope the size of the Earth, rather than simply a single radio telescope to actually determine this is what you're actually observing. So it needed to be a huge one simply because this is only tens of micro arc seconds in size. The accretion disk in the Milky Way is expected to be a lot smaller, but of course the center of the Milky Way is a lot closer than the center of this distant M87 galaxy, and so excuse me, even though it's 1,000 times smaller, it's 1,000 times closer, and therefore the size on the sky is very similar. So what is it we think we're looking at in this orange donut that appears to have a shadow in the middle and is brighter on one edge than the other edge? Well, this simulation gives us an idea of what we think we're looking at. Here, the accretion disk seen from above is simply circular, but the accretion disk seen from the side doesn't simply look like Saturn's rings might because of the distortion effects of the gravity of the black hole. So in other words, we can see the far side of the disk as well as the near side of the disk. Not only that, but we can see the top of it and the bottom of it at the same time. Because of the distorting effects of the gravity of the black hole, light from the far side of the accretion disk is being bent over the top of the black hole and underneath the black hole. So we can't see anything in the middle. There's a shadow region because no light can come from a region particularly close to the black hole, but we can see all sides of the accretion disk coming at us. And notice that some parts of the accretion disk look brighter than others. In this case, it's brighter on the left than it is on the right because of the way the accretion disk is rotating. So that's why we see something that looks like a donut, a shadow in the middle, because light finds it very difficult to come from that region towards us because of the bending of space by the black hole in the middle, and it's brighter in different regions because the accretion disk is rotating. The supermassive black hole at the middle of Sagittarius A, in other words, the middle of our own galaxy, at first sight looks very similar, even though it's 1,000 times less massive, it's 1,000 times closer, but it tells us that the physics must be essentially the same, because although it's 1,000 times less massive, we still seem to get the same sort of orange donut indicating the accretion disk forming around the black hole. It has a different arrangement of light areas and dark areas, and if we were to watch this, then there's the possibility of seeing that structure change. And some of the follow-up measurements that are being made of Sagittarius A star are looking for signs that this accretion disk is rotating. Being a lot smaller, then the matter within the accretion disk is a lot closer to the black hole, will be going around the black hole a lot faster, and so there will be changes on an hour-by-hour basis, which is one of the reasons this observation was more challenging and hence took longer to analyse than in the previous one, because you can't simply average over a few days of data, because over a few days the accretion disk will have changed because of the speed at which everything is going around this black hole. Data was also taken as a function of polarization, which gave us an indication of what magnetic fields might exist inside the accretion disk. And it looks like that overlay that you can see here is an indication of the directions of the magnetic field within the accretion disk itself. We really need more data to tie down with more resolution what the magnetic field in these systems is actually doing. And it may well be that the magnetic fields are crucial to understanding the jets that can be produced by supermassive black holes. Just to remind us that the scales are very different, when you put them side by side, they look a similar size, but only because the centre of the Milky Way is 1,000 times closer than the centre of M87. But if you think of it in terms of actual scale, the accretion disk around M87 is huge compared to Pluto's orbit, for instance. And that gives you an indication of how far Voyager has moved from the centre of our solar system. If the M87 black hole was placed where our Sun is, then Voyager would have just reached the accretion disk. Compare that with Sagittarius A, in which the entire accretion disk would fit inside the orbit of Mercury. So you can see a huge difference in actual size, even though they appear the same size or a similar size in the sky. A reminder of just how enormous some of these jets produced by supermassive black holes can be. If we have a look at Hercules A, there's the Hercules A galaxy in the middle, a very large, apparently elliptical galaxy. Just to give us an idea of scale, it is probable that if this galaxy just below it in the image, if that's at a similar distance to Hercules A, then that galaxy there is probably about the size of the Milky Way. So you can see Hercules A itself is huge compared to the Milky Way. But the supermassive black hole at the centre of Hercules A is producing so much energy that the jets produced actually extend way beyond the actual galaxy itself. And if we look in the radio, we can see these huge jets and these shock waves that are produced by whatever is coming out of the black hole, whatever these particles are. They are slamming into the intergalactic medium and producing these shock waves that we can see to the left and to the right. And given that the Milky Way is many hundreds of thousands of light years in diameter, you can see that these jets produced by the black hole, even though the black hole might be only the size of the solar system, the jets produced by the black hole are millions of light years across. So it's a reminder of just how energetic supermassive black holes can be. If a supermassive black hole is feeding voraciously on the surrounding gas, in other words, if lots of matter is falling into the black hole, it can produce huge amounts of energy, and we call those active galactic nuclei. And the most energetic of the so-called AGNs are what we call quasars. They emit so much radiation that they can be observed even over distances of many billions of light years. And a few years ago, I told you about how during a COVID lockdown, I imaged a quasar, which is at a distance of 25 billion light years. But still, it's possible to image this object, even without a telescope. This was just a camera and a lens. It's possible to image a quasar at a distance of billions of light years, many billions of light years, simply because of the sheer amount of energy that are coming out of these objects, these quasars. And this is so remote, this particular one, at a distance of 25 billion light years, this object is so remote it's actually receding from us at something like twice the speed of light. A reminder of just the enormous amounts of energy involved. So we know supermassive black holes have been found in a large number of galaxies, and here is a plot of the black hole mass that's been determined, and on the horizontal axis the mass of the galaxy, or more strictly the mass of the bulge in the galaxy rather than the amount of mass in the outer spiral arms. So in the bottom left we can see the Milky Way, a relatively lightweight galaxy with a modest 4 million solar masses black hole. And in the top right we see M87. That's why it was chosen, because we know it's a very massive galaxy with a very massive 6 billion solar mass black hole at the centre. And there appears to be this relationship between them. They're a little bit loose, but it looks like the biggest galaxies have the biggest black holes and vice versa. The smallest galaxies have the smallest black holes. So we know the size of the black hole is related to the size of the galaxy. So we know there's a causal relationship between them, but we don't know which way round it is. Did the black holes form first and then the galaxy effectively form around the black hole? Or did the galaxies form first and eventually stars died and produced black holes which eventually merged together to make a supermassive black hole? In other words, it's a little bit of a chicken and an egg problem. We know they form, and we know they form on similar timescales because we know that over billions of years we see galaxies which are massive and they contain massive black holes. But it's not really obvious as to what the causal relationship is. That's one of the reasons the James Webb Space Telescope is looking back in time as far as possible to see the very earliest galaxies, to see if those very early galaxies had supermassive black holes. Is there evidence that the earliest galaxies had supermassive black holes, much as they do today? Much as they do today. And at the moment, the jury is still out, but it does look like supermassive black holes formed very early. It's not simply a question of galaxies formed and stars died, and then eventually those stars that produced supernova and black holes, eventually they merged together to make supermassive black holes. So it looks like supermassive black holes have been at the centers of galaxies ever since the very early universe, but the jury is still out on that. Let's finish by looking at the C of the ABC. Galaxies effectively evolve by colliding with other galaxies and ultimately merging together. So snapshots like this can be deceiving, because we look at a snapshot and we think that's very nice, lots of spiral arms, and we sort of know that galaxies are rotating, but we don't realize just how dramatic it is in terms of how galaxies interact with each other. It's only through interactions that we can understand why galaxies end up looking the way they do. So some snapshots make that clear. We clearly have, thanks to the Hubble Space Telescope and others, we now have lots of examples where we're seeing not simply galaxies in isolation, but we're seeing galaxies interacting with each other. I showed one very early on, the Rose galaxies, in which what appears to be a spiral galaxy is interacting with its neighbour and becoming rather distorted. So we have lots of snapshots telling us that interactions appear to be important, but it's only really when we run simulations that we can appreciate just how the interactions and the collisions and the mergers of galaxies actually affect their evolution. So here again is a TNG simulation on a somewhat different scale now, and we're seeing a whole load of galaxies coming in from the top and a whole load of galaxies coming in from the bottom, and we can see thousands of galaxies. But notice the two large galaxies close to center are now gravitationally attracting each other. They've just passed each other, and then over a few 100 million years, perhaps a few billion years, they merge together, and the supermassive black holes at their centers will ultimately merge together. If we run that simulation again, we can again see on a spatial scale here of megaparsecs, we can see lots of small galaxies, some of which are getting eaten up by the larger galaxies, and we see that some galaxies are getting very distorted, like the one on the left there, and as these two big galaxies towards the center merge together, they merge into an even larger galaxy and again start to gobble up some of the smaller galaxies. And that's pretty much what we see when we look out into the universe. We see large galaxies which quite often are surrounded by lots of smaller galaxies which they are ultimately in the process of eating. Crowded galaxy clusters like this one often are redder than the more bluer spiral galaxies, indicating that most of these galaxies are elliptical galaxies. So why do we tend to see lots of galaxies in galaxy clusters that look elliptical rather than spiral? Well, it's because when you get a galaxy cluster, they are relatively crowded in terms of how many galaxies there are per cubic megaparsec, if you want to think of them that way, and hence they're much more likely to collide with each other. And when you get spiral galaxies colliding, you tend to end up with elliptical galaxies resulting. So in that sense, it's no surprise to find that when you look inside dense galaxy clusters, you often find large populations of elliptical galaxies rather than spiral galaxies. And we think this is going to happen with Andromeda and the Milky Way. We are gravitationally bound to Andromeda, so we're not receding from it because of the expansion of the universe. We are gravitationally coupled to it, and in a few billion years, as you can see from the counter in the bottom right, the two galaxies are going to pass through each other. So Andromeda will pass through the Milky Way. It's unlikely that any particular stars are going to collide with each other. The Sun might be dragged out of the Milky Way, but if it happens, the planets will probably just go with it. And eventually, the Milky Way and Andromeda settle down into one big galaxy. And if you wait long enough, M33, the Triangulum galaxy, will join them as well. If we think what that might look like as seen from the Earth, so at the moment we see the Milky Way as a band across the sky, and we see the Andromeda galaxy as an object a little bit bigger than the full moon. But if you wait a few billion years, well, the Andromeda galaxy is going to get larger in our sky as it comes towards us. For those of you who like to photograph the Andromeda Galaxy, in a little while you're not going to need a telephoto lens. It won't be long before you need a wide-angle lens to get it all in as it comes towards us. And as the Andromeda Galaxy passes through the Milky Way, it's ultimately going to be impossible to tell which star is which. And as the two galaxies pass through each other, there is going to be a riot of new star formation. Stars are unlikely to collide with each other, but the gas clouds of one will interact with the gas clouds of another, and those gas clouds will collapse and produce new stars. So all of the pink we can see here indicates new star formation. After a little while, the two galaxies will pass through each other, and probably the spiral arms of both will be thoroughly disrupted. And in a little while the two will settle down into something that may well be an elliptical galaxy. After 5 billion years, this is indicating that we're in something like an elliptical galaxy, but there's still a concentration over here and a concentration over there, indicating that we have a supermassive black hole with lots of stars orbiting around it, and a supermassive black hole over here with lots of stars orbiting around it, because the two black holes in Andromeda and in the Milky Way will orbit each other for quite a while before they eventually merge and produce an even larger supermassive black hole. What are we going to call this new galaxy? Milkdromeda or Andrilke or Androway? We've got plenty of time to figure out what the new name is going to be. We've got 5 billion years before we have to worry about what the new name is. Perhaps when these two supermassive black holes get close to each other, there's going to be so much matter falling into one or other of the supermassive black holes that we could end up in a galaxy which is turned into a quasar. Remember, a quasar is a galaxy in which huge amounts of matter are falling into the black hole at the center, and that's producing a huge outflux of energy, some of which is in the form of these jets that are produced by mechanisms that we are still in the infancy of understanding. So maybe we will end up in a galaxy that turns out to be a quasar. That's conjecture at the moment. We don't really know how that is going to look. But we do think we understand the basics of galaxy evolution thanks to some observation and thanks to a lot of simulated calculations of how we think things are behaving on the large-scale structure of the universe, as well as the stellar scale of how that affects the way galaxies are produced under the influence of gravity. So we know galaxy is responsible for the accretion process, but we know supernova and black holes ultimately stop some of that collapse under gravity, because both supernova and black holes produce outward flows of matter and radiation that can stop the collapse. And we know that ultimately, on the long scale of the universe over many billions of years, we know that galaxies interact with each other because the distances between galaxies are not as large relative to the size of a galaxy as, for instance, stars are. So our sun doesn't interact with Proxima Centauri, but we would expect galaxies to interact with their neighbours. And the interaction and the collisions and the mergers of galaxies ultimately are responsible for how galaxies behave over many, many billions of years. So next time you're looking at a galaxy either through a telescope, or maybe you're imaging a galaxy for yourself, or maybe you're just thumbing through a magazine admiring images such as those produced by the Hubble Space Telescope or the James Webb Space Telescope. Next time you're looking at a galaxy, perhaps just give a thought for the A, B, C that are responsible for how the galaxies ended up looking the way they do. Thank you very much.